Hey folks, welcome out here to a great specialized segment, Friday edition of TN Learn Mathline. I'm your host, Ernie Roberts, and I will be with you for the next few minutes, and we were going to be doing some great stuff. You might want to get pencil, paper, even a graphing calculator, or just calculator, and today maybe a little graphing paper. Yes, it does. Oh, notebook paper too. But anyway, we're going to sit back, relax. We're going to do some fun math things today, all right? And get you a chance to learn a few things in the same process. So let's see what the topic of the day is. Let's see what we got going here. Looks like we're going to pick up the pieces. You know, we've been doing piecewise functions. Today we're going to take them a notch further, view applications, and try to get in some graphs for them, all right? So be sure to take, like I said, get that graphing paper, those graphing calculators, all sorts of good things ready to go today. We're going to have a lot of fun. Let's see what our first problem is. Now, when we talk about piecewise functions, first of all, we got to remember, how do we do this function notation? That's what this f of x and g of x is all about. Don't get excited. F is just simply saying first function, g is my second function. It's just a way to name it. So these letters sometimes on the outside will give us an indication of what this function is about, all right? In this case, we're just labeling it to distinguish that one is f and one is g. It also helps us when we're looking for things that we need to substitute. Notice we've got f of negative 4. That means we're going to say pick the f function, and instead of an x, we're going to put a negative 4 everywhere we see the x. That's the deal. So let's go through that first part right here. Let's take this function of negative 4, all right? And we've got f of x equaling to x squared minus x plus 2. There we have it, all right? Now, when we look at that, you say, Ernie, that's like a lot of x's. There's squares and all sorts of things. And notice we put f of negative 4 right in there, and that's going to give us negative 4 squared. Now, notice I put a parenthesis around it because I want to make sure we take that negative and square it also, minus that negative 4, put it in a parenthesis again, plus 2, all right? So again, let's see what we've done. We've substituted negative 4. We're going to square it. We're going to subtract our negative 4, and then we're going to add 2. Now, everybody knows out there, I hope tuning in today. If not, we'll tell you. When we have subtracting a negative 4, that's like adding a positive 4. So we're going to put plus positive, all right? Now, the other thing I told you, be careful. We've got to put that negative 4 in a parenthesis because when we square a negative 4, my friends, it's not 4 times 4 and then stick a negative. No. It's a negative 4 times a negative 4, which is going to give us 16. All right, and this is going to go give us 4, and this is going to give us 2. So everything became positive here, right? Because 16 plus 4 plus 2, which gives us a nice total of 22. Now, let's look on the other side of the picture here. We've got the g function for negative 2. Sometimes we call that a g of negative 2. So let's write our g of x function, and that will equal to 1/2 x, make that look like an equals, 1/2 x, and that is going to be with a minus 4 attached, all right? So we're going to put in a negative 2 everywhere we see an x. So this one's a little easier, just a linear function, and we have a 1/2 times that negative 2, and we're going to subtract 4. So we take 1/2 of negative 2, folks, it's just like take half of 2, but this time it is a positive times the negative, so we are going to end up with negative 1 minus 4, which is going to give us negative 5. That's like adding 1 and a negative 4 together. Negative 1 and negative 4 together, we get the negative 5. And there you are. So that's just a quick review over functional notation. We're going to use that quite a bit today. When we look at the piecewise functions, the concept of a piecewise function is that we'll have more than one function. However, we're going to try to graph it at the same time, okay? So in other words, it's got basically maybe 2, 3, it could have 4 or 5 parts. It just depends on how many different specifications you're given in the problem. So let's take a look at an example here, all right? Piecewise functions. Notice we've got 1, 2, 3 situations. And you say, well, Ernie, do we do them all at the same time? No, if we did them all at the same time, for all the domain of all real numbers, we wouldn't have functions. We'd have this vertical line test going crazy when we try to graph them. So what we've got to do, we've got to specialize it. We've got to say, for example, here if x is less than 0, that means negative numbers, all right? For any negative values of x, we're going to use the 2x plus 1. For any values that go from 0 to 3, and they're inclusive means they're going to include the 0 and the 3, we're going to say the answer is 4. just equals 4. We're not, x has no effect except to say, we're going to say 4 for y. 4, 4, 4, all right? Now, the next part, if we are greater than 3, in other words, we've covered all the options. This was less than 0. This touched 0 all the way to 3. Now we're going to pick up for the numbers that are greater than 3. Now we can look at that function, negative 2x plus 2. So the question is, looking at what I've given you here, what are we going to do with these function values, all right? So it says f of negative 1, or a function of negative 1. Which function do we choose? Well, it's less than 0. It's a negative. So we're going to go to this first guy, where if x is less than 0, we're going to pick this one up. So here we have it. We're going to take the 2 times our negative 1 plus 1, all right? So at this point, for negative 1, by the way, that's our x value. Our ordered pair that goes with it will be, let's see, 2 times negative 1 gives me negative 2. Add 1. We got negative 1 right there. You go. All right? Now, for f of 0, remember what I said. If it is 0 to 3, inclusive and anything in between, the answer is automatically 4. We don't have to figure anything out. It tells us, use 4. We're done. Okay? So that ordered pair would be 0, 4. We were looking at ordered pairs on these. Now, what about our last situation? How about the function of 4? And I'll look at that. Which of these requirements does it meet? Well, it's greater than 3. All right? So we're going to use this function, this negative 2 times 4 plus 2. All right? That's our storyline here. So we put in the 4, and we have negative 8 plus 2. And that's going to give you negative 6. Ordered pair for this one would be 4 and negative 6. So that's what we're looking at, folks. That's the idea of a piecewise function. 3 different functions with different specifications of the domain. Now you may ask, do they have to be all real numbers used? No, sometimes we have situations where we don't have any negative involved, all right? All the values of x may be positive based on time moving forward, all right? We'll see some examples of that, all right? So it doesn't always have to be all reals, but one thing does have to happen is when we graph these puppies, and that's what we're going to do, when we graph these, we do need to have, let me get my graphing paper here, folks. There we go. We're on good, on good. There we are, all right. Had to do a little twisting and turning. It's Mathline here on a Friday. It goes with it. But let's talk about how do we graph, and let me put those back up here again. This just takes a lot of space, so let me try and do the best we can. So remember we were going to use f of x to equal 2x plus 1 if x was less than 0. All right, that was our first stipulation. Our second one was we were going to use f of x equals 4 if we had 0 less than or equal to x less than or equal to 3. All right, that was our story. And our third one was using that f of x equaling to negative 2x plus 2 for x being greater than 3. All right? So what we've got, we're going to try to put these things all on the same graph. That's the idea, all on the same set of axes here, all right? So first of all, we have this boundary here. Where x is 0, that's basically the y-axis, all right? And according to this, we said we're going to use 2x plus 1 as long as it is less than 0. Well, first of all, I'm going to put a 0 boundary in there and see what happens. If I put in 0 for x here, I'm going to get 1. So I know that I have 0 and 1, but folks, we're going to make an open circle there because we don't include the 0. We get right up to it, but that's going to be an open circle, by the way. That's an open circle right there, okay? Now, what are we going to do from here? Let's try another number. Let's go to negative 1. If I put a negative 1 in here, I'm going to be down at negative 1, negative 1. You see, when we put a negative 1 in here, it's 2 times negative 1, which is negative 2. Add 1, you get negative 1. So here we go. And now I'm starting to create what this function's doing. It's linear, so I'm just going to keep the pattern going here. Put in a negative 2, we're going to bring it down to negative 3. And from here, we're going to connect just like we would a linear fashion. In linear fashion, there we go. It just keeps going and going and going because we did not have any restrictions on the negatives. We just keep going to the left, which means it's going to keep going down, keep going down, keep going down, all right? And you say, well, Ernie, what about that open circle? Why did you do that? Because we don't want to include 0, but we're going to match it right up as close as we can get. You see, we can use we can use the very, very close, like maybe negative 0, 0, negative 0.00000, you know, get the idea. 1, so we get very, very close to that, but that's why we have the open circle there. It says it just doesn't include that point, but any other point on that line is fair game for this part of the function. Now, the second part says we're going to go between 0 and 3. And according to this, the answer is we're going to get 4. All right, so since I'm counting up by 2s here on each of these, let's see, counting up by 1s, excuse me, I've got 1, 2, 3, 4, and this says we're going to allow it to include that. So we'll put a closed circle there. All right, put a closed circle there. And for our next 3 moments, we go over 1, 2, 3, another closed circle, and there's our line segment that connects those. Because no matter what number I pick in there, the answer is 4. All right? Isn't that nice to always know the answer is going to be 4? At least if you're between 0 and 3 on this one, all right? So see what's happening? This function's a piece, this function's a piece. We've got 1 more to go. What happens when we are going to be greater than 3? So what I'm going to do, I'm going to first put a 3 in there, and at 3, we are at negative 4. And I'm going to put an open circle there because I don't want to include 3. See that? Don't want to include 3. Now this being negative, this is going to go way off my charts here. So let's see what happens if I go with the number 4. All right, putting in the 4, which we did on our previous problem. 4 gives us a negative 6, so I'm going to go over 4 and down 6. And you get the idea. This is linear. So once we connect these two right here, it's going to keep going into the negative direction also as we keep moving along. So you say, Ernie, how do we call that a whole function? Remember what I said, this whole thing needs to be passing the vertical line test. So here we go. Remember, the vertical line test means you cannot hit 2 points vertically at a time. So here we go. Follow my rulers. It's getting there. All right, this is where we have our first wonderment. But see, because this is open, there's not 2 points. There's still just 1 point that it's touching, okay? So vertical line test is satisfied there. We still have a function. Keep moving along. Here's our other possibility right here because there's an overlap at 3. But see, that's an open, that's closed. So that's why we have to be very careful about our stipulations or our domain. We cannot overlap domains because then we lose the function idea. The whole idea of piecewise function is you've got 3 different situations that cover whatever the domain is that you're wanting to do. You cannot repeat. In other words, 0 cannot give me 2 different values for y, okay? Otherwise, it doesn't make any sense. Which one do you choose? All right? It's not a function. It's not a function. It's got to follow the function rules. So that's a look at the graphing. That's a look at our graphing. So let's take a look at another piecewise moment here. All right? Let's take a look at this next one here. We've got y equals x plus 2, or f of x equals x plus 2 there, as long as we are what? Less than negative 2. In this case, we are going to take and look at being 2x minus 1 if we're greater than or equal to negative 2. Now, you said, Ernie, there's just only 2. Well, like I said, there could be 2 or more when we're doing piecewise functions, all right? So let's take a look at how these are going to look. So if guys give me just a second here to shift out, bring the graph paper in. Thank you. And here we go. Got our graph paper. This is one of those gets a little crazy here because we've got so many things going on. Let's take a look at it now. First one we said was basically f of x is equal to x plus 2. That's what a piecewise function notation tells us. If we had x less than, just less than, not less than or equal to, negative 2. The other side, we're going to use the f of x function to be 2x minus 1 if x is greater than or equal to negative 2. Once again, that is just less than there. It is not equals to, okay? It's looking worse and worse, isn't it? All right. Very important, though, because we don't want to have problems where we have to worry, well, which choice do we make? Because if you've got 2 options, there's no point in the problem, all right? So we got to keep the functions going straight there. So the idea, first of all, is at negative 2, what's going on? Because that seems to be where the magic is all happening. So let's go back to negative 2, and let's put it into this first function. Now, I don't want to include negative 2, so I'm going to use an open circle. So that point with negative 2 plus 2 is going to be at negative 2, 0. We're going to put an open circle right there. Make a big open circle, all right? That basically means we get real close to negative 2, but we just don't quite tap it, all right? Now, on our other one here, as we get greater than negative 2, we are going to go ahead and put our negative 2 in for this function. And by the way, this one's going to be included, so we are going to be able to do a closed circle on this one, all right? So let's see what happens. Put in -2. I'm seeing -2 and -5, okay? Because we say 2 times -2, that gives us -4. Subtract 1, we're going to be -2 and 5. So here we go. To the left and down, 1, 2, 3, 4, 5. Solid circle there, folks, solid circle, all right? Now, let's start moving on to the right. How about it? Let's see what happens at -1. That's to the right here. So we put a -1 in there. We're going to be at -3. So I'm looking at -1, -3. Starting to plot the points here. And do one more, easy one. How about 0? 0 is greater than -2. So I put a 0 in there. I'm at -1. You get the idea. Now, here's the deal. You say, well, Ernie, what's going on here with this open circle? We didn't go any farther, did we? Let's see what happens on this open circle. We have -3. Let's go for some numbers that are less than 2. By the way, this one is already in good shape. Put that one up through there. Let's look at this one over here now. Putting in -2, we got that open circle. How about it? Let's put in -3. We'll go up. We'll go down, excuse me. We'll go down 1. And then put in -4. We are going to go down 2. Get the idea? And this time, the graph is going in this direction, all right? In this manner of speaking, down that way, all right? So now they aren't parallel. This one's got a different slope. This one's got 2, and this one's got a slope of 1. They look like they could be, but they're going to cross somewhere on out there in the great big beyond, but not sure where, okay? But anyway, that's very careful there. And when we look at that, notice here's where we could possibly fail the vertical line test, but that's closed. That one's open. We have a piecewise function, all right? So again, it's about putting them into 2 separate corners, all right? You say, well, Ernie, do we use this stuff? Do we use this stuff? Yes, we do. Yes, we do. Let's talk about our next problem here. Let's look at this little application here. I told you we try to get a couple applications there. Rates in a parking lot are $1 per half hour up to an $8 fee daily, all right? What is the parking fee for the following times? So in other words, if you spend an hour and 30 minutes, or do you spend 3 hours and 40 minutes? And here, 3 hours and 59 minutes, all right? So if you think about it, when you go parking, you pay the meter, or you pay the meter, it goes down by minute, by minute, by minute. But if you go to these pay parking lots, you're paying per half hour or hour, and sometimes you just pay all day, all right? So let's see what happens on this. According to this, it says you're going to get per half hour. Now, you get the dollar for those first 30 minutes. You hit 30, you're still at $1. You go over 30, you're now paying $2, okay? 31 minutes, you're now paying $2, and on up the ladder, okay? So at 1:30, we're going to call it, what's the function of 1:30? That's our variable, okay? In other words, we want to know how much time. We're going to call this function of time. We can call it f of t if you wanted to, all right? So f of t being 1:30. Let's see what we have going on here. That basically means 3 half hours. And for every half hour, you're going to pay $1. So your amount would be $3 that you would owe the parking attendant because you have used 3 half hours, all right? Now, what about it if we had, you spend there 3 hours and 40 minutes, all right? And you're going along there, you're saying that's pretty cool. Well, you got 3 hours, that's 6 half hours, and you get another half hour plus 10 minutes. Well, the 10 minutes is good. That's kind of freebie for you, I guess. But when you get to this point, it's going to be $7. Be $7, all right? Now, from here, how about it? Let's look at this 359. And where would we go? Well, looks like we're still at $7 because we're not quite at 4 hours. We have to hit that 4-hour bunch. And even at 4 hours, you'd still be at $7. Or would you be at $8? Ooh, that's a good question. Let's see. How many half hours are we spending in there? Actually, we're going to go $8. We're going to go $8. It looks like. Because that's going to be, or is it 7.5 hours? Boy, I have to think about this. That's 7.5 hours. So actually, we are still, what are we looking at? We're still looking at not $8 here, $7. You've got to get to 4:01 before you're going to be owing the $8. So up to 4 hours. Up to 4 hours, would that be right? Boy, it gets kind of tacky here, kind of tough here. Actually, let's go back a minute on that. Let's think about that for a minute, folks. 3 hours and 40. Okay, you hit your 3-hour block. That was 6. 3 hours and 30 minutes. You hit 7. Until you get to $4, that fourth dollar, that's when you hit that maximum 8. All right, so up to you get $1 per half hour. So once you get to, you got $8 there at 4 hours and 1 minute. Okay, that's when you're going to be paying. And from there on, it's going to be $4. So it's like what we call a step function there. All right, so it goes flat, then it goes up, up, and up. So it's called a little step function. As you move along, you pay the same value for different spaces. All right. Now, let's look at one more type situation that might be in there. See how we do here. It says if less than 50 shirts are ordered, the shirt cost is $8. If 50 to 100 shirts are ordered, the cost is $7. And if more than $100, the cost is $6. All right. And says we're going to graph the relationship, but first we're going to make a table. We're going to make a table first. All right. So we're going to call this. How about it? It's going to be a cost function, so we'll call it C. And we'll let S be for shirts, okay, for the number of shirts, So in this case, let's see what we're going to do. We got 3 options. First of all, if less than 50 shirts are ordered, the cost is $8. All right, so there we go. There's your $8. And that is for our S being less than 50 shirts. Make sense? Makes sense. That's an S, by the way. Sometimes it looks like a 5. Now, what about our other side over here? If it's 50 to 100 shirts, the cost is going to be $7. And that is going to be 50. And we're going to, by the way, include 50 on that, all the way up to 100 shirts. You're going to pay $7. And the next part would be $6. If your S is greater than 100 shirts. Now looking at this, again, it says if less than 50 shirts are ordered, the shirt cost is 8. If 50 to 100 shirts are ordered, the cost is 7. And if more than 100, the cost is 6. Folks, this is called what we call buying in bulk. If your t-shirts, let's say you're doing this for a club, the same thing would hold true. The more shirts you order, usually the less cost it is. But there's going to be what we call price breaks. We call it a price break. At a certain point, that price drops. And then at another point, it drops. So, if you ordered, let's say, 99 shirts, all right, 99 shirts, cost being $7 a piece, or even 100 shirts at $7 a piece, you might as well go ahead and order 101 because you're going to get a price break at that point, all right? So that's the idea. So let's take a quick look at how this is going to graph out, okay? We've got to move along here. The first things first, we're going to go across the axis here. I'm going to let this thing give us, we're going to let this thing go by 50s, all right? So this will be 50, this will be 100, 150, 200, you get the idea, all right? Now, over here, going up, we're going to let the cost go in terms of $2 each on the axis. You don't always have to count them all by 1, by the way. So let's go 2, 4, 6, 8, 10. That's going to be our cost. All right? So from 0 to 50, by the way, we don't want to quite get to 50, do we? So we're going to put an open circle there. But 0 to 50, your cost is, not there, sorry, it's going to be $8. There's our open circle, all right? There's our open circle right there. So just forget that, folks, that's gone. And we're going to say anything from 0 to nothing. Well, you're not going to buy 0 either. So there you are. You got it right there. That's your little step right there. It's flat. It's flat. From 50 to 100, that's our next bracket, okay? From 50 to 100, we're going to say, that's, by the way, that was with equal, so we're going to open the dots there. We're going to close those circles, and we're going to have it going like that, okay? And anything above 100, we'll put an open circle right there, and it just goes on, because it depends on how many shirts you're going to order. You've got it made there from there, all right? So this is what we call a step function, all right? Because it's basically looks like steps coming down, all right? And our parking lot graph would have been the same way if we'd done that half hour. Each time would go up, 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 all right? Because your total cost would be there, and it would stay steady for a certain amount of time for that half hour, okay? So there we have, that's our story, and good stuff there, good stuff there. I always like for you to see that when we talk about these functions, they are real world. And by the way, you can check this one out on Facebook if you want to. Again, www.facebook.com, as we picked up the pieces today. TN Learn. Also YouTube, we've got that going on. You might see this also, www.youtube.com/TN Learn. Woo, it's Friday, folks. And we picked up the pieces pretty well today. Hope you've had a good time with us. See you again Monday.